When a wave passes through a medium, you can say that there is energy transfer through the medium. For example, if we create a pulse or on the string, and on this string there is a mass m attached to this point of the string, you can see that when the pulse moves to this point, the mass m will move up due to the displacement of the medium here. So it means that initially the mass m is at rest, but it moves up when the pulse passes to this point. It means that the mass m gain the kinetic energy because it has a velocity, and also it gains the potential energy because it changes the vertical position. So it means that when the pulse passes through the point here, it transfers the mechanical energy to the mass m. So we can say that the disturbance, the energy from the source, it comes from the disturbance of the medium, can transfer to the medium in the form of the traveling wave. Now, let us see in more detail of the energy transfer on the spring. Okay. Let us consider a small element on the medium. For example, this element, and when the wave passes through this element will move up and maybe move up and down, and it means that the energy is transferred through this element when the wave passes through. Okay. The energy of this element, of course, you have two components, that is the kinetic energy and the potential energy. Let us first looking at the kinetic energy. We can see that from the definition of the kinetic energy, the kinetic energy of the element dm can be expressed as dk. We use d instead of just k to emphasize that this is the kinetic energy of a small element of mass dm only, and dk is equal to the half of the mass of the element, which is dm, times the velocity. And since this is a transverse wave, so it means that the displacement is on the vertical direction only, so we have the vy square here. We also have the potential of that element, which is equal to the half of the this is a half of the omega square dm y square. Okay, this term, we assume the potential energy to have this term because we know that the element on the wave, when the wave passes to the medium like this, and if we look at a small element on the curve, on the wave, on the medium, we can see that this element will move up and down when the wave passes through this point. the angular velocity of the oscillation is omega. Okay, and since the motion of the medium here is very similar to the simple harmonic motion, this motion is simple harmonic motion, so we can model the motion of the medium here as the oscillation of the object of mass dm attached to the spring with spring constant equal to the omega square and the mass of the element dm is the spring constant. Okay, we use the word spring constant here in the sense that because the motion is similar to the simple harmonic motion, so we can use the model of the mass spring to explain the motion of the medium here. Okay, now this is the kinetic energy and the potential energy of just one element of the wave. Okay, now if we want to calculate the total energy along the wave, maybe the total energy that the wave carry in one wavelength, that is more useful to do that. So the energy, start with the kinetic energy. We have that the kinetic energy in one lambda is mean that in one wavelength is equal to the summation of the kinetic energy. Okay, which equal, because we are interested in one cycle or one wavelength, so we do the integration from 0 to 1 wavelength of dk, and I will substitute dk here. It is a half of the dm vy square. Next, we know that the Vy is equal to the the Vy can be expressed as the cosine function. So this equation will become the integral from 0 to lambda of the half of the dm. Now we change the notation a little bit. Since dm is a mass, we can say that we can write this as a mu dx. Dx is the length of the element, of this element that we are interested, and Vy, we have discussed before about the form of Vy, so we can put it here. It's equal to the minus of okay, write in this minus omega A minus omega A cos kx minus omega t. Okay. Performing this integration will give us the solution as 1/4 of mu omega square a square lambda. Here A is the amplitude of the wave and lambda is the wavelength of the wave. We can also do this for the potential energy, and that left to the exercise for you. But the final result is that the potential energy in one wavelength that the medium received from the wave is one-fourth of the mu omega square a lambda. The total energy of the wave in one wavelength, total energy in one wavelength is thus Ek is equal to the E lambda is equal to the K lambda plus U lambda, which is equal to the half of mu omega square a square lambda. This expression is the total mechanical energy that's stored in a wavelength. Stored in the wave within one wavelength. Is stored in the wave within one wavelength. The energy stored in the wave itself is interesting, but sometimes we are not interested in the energy in the wave only. We also interested on the rate of the energy transfer, in the traveling wave. The rate of the energy transfer can be calculated like this. Assume that we have the wave and we want to know the energy transfer through this point. Okay, we know that for the wave of the wavelength lambda, this region of the wave within the one wavelength will pass to this point in the time equal to the period of the wave, right? Because in one period, one wavelength on the wave will pass to this point. So we have that the power that delivered by the wave is equal to the total energy of the wave in one wavelength divided by the time of the wave in one wavelength will pass through the point like this, and that is a period of the wave, and this equal to the half of the mu theta square a square lambda over t. However, if we look at this term, lambda over t, we can see that this term lambda over t is the velocity or the speed of the wave, because we know that a portion of the wave with the length equal to lambda will pass this point like this in time t. So the speed of the wave is a motion of the wave divided by the time taken for the wave to pass to this point. So this lambda over t is the velocity of the wave. So what we have is that this equal to the half of the mu omega square v. Okay, oh, I missed a square too. So this is the formula for the power that deliver through the wave. Okay.